you figure out what causes the angle to change, I don't know if it's a powerful magnetic field. My goal is not to alienate or to call science closed-minded, because it isn't. I just had this conversation with a friend of mine who spoke to a really famous scientist, and he told me that what that scientist said about my work. And I said, well, first of all, like, I know about his work very well. I know, but and then what I said is, I have complete respect for this. It's not closed-mindedness. It is a certain kind of rigidity that is very important, because what science came into this world to do is to combat foolishness, which there's a lot of foolishness. And up until we didn't develop this system of certain kind of rigidity, we couldn't build what we have today. We would never have the computer we're talking through right now if we would not have this kind of rigid way of what works and what doesn't work. Okay, because of that, I have complete respect for that. So I'm constantly trying to play this central role where I'm making the information a little bit more palatable, both sides, because I'm trying to bridge. I'm trying to say, no, we're saying the same thing. There's a place for this and there's a place for this, and it's not always in the same instance, and they're both important, and we have to kind of bring the two hemispheres together. From a theoretical side, one of our postulations now is that, so the reason the laser works is because, so if you look at a hologram, a regular hologram, the way it works is that you have a source light coming from here, and then it's being split to two by a beam splitter, right? So it goes into two. And then this beam goes through a set of mirrors and then hits an object here. And then after it hits the object, it hits the screen where the information is being recorded. So it goes here, mirrors, object, screen. This other beam, which is the same beam, it's just the other part of it, also goes to a set of mirror. And then it meets itself, the other part of itself that's split, after it already hit the object. And it basically registers, if you put it at the exact right angle, it registers the phase shift. So this is the amplitude, which means that how bright or dark the pixels are, depending on the density of whatever material it hit. And here you also have the phase shift, which allows you to have this illusion of a three-dimensional image. So when you remove the source light, this part of the beam, and you remove the object from this side of the screen, you can still see as if the object is there, and you can see it in its full three-dimensional glory. Right? So the reference light is key in registering the information by giving, that's why it's called the reference light. It gives the reference of the exact angle with which the other information is encoded. So what I think is that our consciousness, our perception, is that reference light. And this is the source light, whatever you want to imagine it is. But whatever it is, where your consciousness meets the source light, which you can think of as the light that is coming from everywhere in the universe, stars everywhere, that is emanating photons. And it hits the sheet where everything is being recorded, which in our case is space-time itself, the bulk. So these three things are in interplay, and I think that's what's going on. And the reason we can see the code is because we are the hologram, and it's an angle thing. So something about when DMT, whatever DMT does in the brain, I think it gives you the ability to have more computational steps per information density, so per time. So it's almost like it gives you the ability to see between the frames. So it goes, you see more frames, okay? And then in addition to that, there's something about the laser, because it's coherent, there's something about the meaning of the angle that allows you to almost, for lack of a better term, to see around the corner. It's almost like usually you're looking at the creation of that instance, that is the physical world, in directly. Now you skewing the angle a little bit to the side. And because of it, you kind of see behind the corner that is all the code that is actually written to make this thing happen on a holographic sheet. So what's beautiful about this is, as wild as that sounds, that's testable. If any of this is true, might not be. If any of this is true, this is testable, because we're talking about angles. So if you figure out what causes the angle to change, I don't know if it's a powerful magnetic field or projecting into particular materials that help it do that, we can then test certain angles. And if we change the angle more, we should have a predictable outcome. We should say, well, we know what a regular hologram does, so it should be something along those lines. You should be able to see some kind of either a phase transition, or you should be able to see some kind of a vagueness that happens, or a splitting that happens. There's something very specific in geometric terms that should happen, and we should be able to play with it both theoretically and experimentally. So now it opens the window for real scientific work around these things. And then obviously, if we can produce something like that overnight, you will get very serious people interested.